The decision speed, V1, is called by the pilot not flying on every transport and corporate jet takeoff. If an engine fails at or before V1, a stop can be made on the available runway. Above V1, a safe stop cannot be made, but an engine out takeoff can be accomplished. If the total distances to stop or to go are equal, this distance is known as the balanced field length. In this video, computer simulation will be used to show how V1 is determined, what it depends on, and practical considerations such as the effect of available runway length and other abort considerations in addition to engine failure. In order to compare accelerate go and accelerate stop distances, we must look at the procedures used to measure them. If an engine fails above V1, rudder pressure is applied and held to cancel out the yawing moment as the takeoff roll continues to VR, where rotation to the pitch attitude that will maintain V2 is accomplished. The accelerate go distance is the number of feet from the beginning of the takeoff until reaching 35 feet. The accelerate stop distance is measured by failing an engine 1 second before the V1 under consideration, in order to simulate the time necessary to recognize that the engine has failed. Then, 2 more seconds are allowed to elapse to simulate the reaction time necessary to take the actions required to abort the takeoff. These actions are retarding the thrust levers to idle, verifying that the ground spoilers have automatically extended, and that the auto brakes have activated at the rejected takeoff setting. The distance from the beginning of the takeoff roll until the aircraft reaches a complete stop is the accelerate stop distance. We will now use computer simulation to see how the stop and go distances are related. This simulation compares accelerate stop and accelerate go distances for a wide-body jet transport making a flaps 5 takeoff. We can select 3 different gross weights, 2 altitudes, and 2 clutter conditions, as well as the engine failure recognition speed, which is 1 second after the actual engine failure. We will set the gross weight to 267,000 pounds and the engine failure recognition speed to 0. This allows us to look at the extremes. We will first look at a single engine takeoff, starting with the flight deck view. Observe how the EPR setting starts off at a low value and gradually reaches the takeoff power setting of 1.43 when the speed reaches 114 knots. This gradual power increase is necessary because rudder authority and nose wheel friction cannot cancel out the yawing moment created by the operating engine on this twin-engine jet with wing-mounted engines. Maximum rudder deflection is held during this acceleration. The minimum speed at which maximum rudder deflection can cancel out the yawing moment caused by takeoff thrust set on the operating engine is VMC ground, which in this case is 114 knots. Since an engine out takeoff can never be continued at takeoff thrust from a speed below VMC ground, the only option is to immediately move the thrust levers to idle and abort the takeoff. Since there is no option to go, V1 can never be less than VMC ground, and therefore the minimum V1 is equal to VMC ground. Notice the unrealistically long takeoff distance, even for this moderate gross weight. We will now look at the accelerate stop distance. Notice the expected result. What we see in this extreme case is that for low engine failure speeds, the accelerate go distance is much longer than the accelerate stop distance. Next, let's look at the opposite extreme, an engine failure at VR. The following simulations are done at 8 times the normal speed, since the final distance is our primary interest. Notice that in this case, at the maximum engine failure speed VR, the accelerate go distance is much shorter than the accelerate stop distance. Therefore, an engine failure recognition speed that makes the two distances nearly equal, i.e. the V1 for balanced field length, must lie between V1 min, which is VMC ground, and VR. Next, let's look at both go and stop distances with an engine failure recognition speed of 129 knots. Since both distances are essentially equal, the balanced field length V1 for these conditions is 129 knots. Until we look at the effect of longer runways, V1 means the value that produces equal stop and go distances. In other words, the balanced field length value. Now let's look at the effect of increased weight. Setting the gross weight to 320,000 pounds, where the V1 is 145 knots, we see the following result. At the lesser weight, a legal takeoff could be made on a 6,500 foot runway, but at this heavier weight, at least 9,100 feet is required. So, heavier weights require longer runways and higher values of V1. Let's increase the altitude to 8,000 feet, where V1 is 147 knots. Since we would need over 13,000 feet of runway, which we don't have, let's reduce the gross weight to 267,000 pounds, where V1 is 131 knots. Notice that a legal takeoff can now be made on this 9,100-foot runway. Also notice that the change in V1 for altitude was only 2 knots for both weights, but the change in V1 for weight was 16 knots, even though the change in distance was approximately 3,500 feet for both weight and altitude. Let's now repeat our takeoffs at 320,000 pounds and 0 feet altitude. Remember that the 9,100-foot runway met legal takeoff requirements. Now let's look at the effect of clutter. Clutter is anything that contaminates the runway surface and affects both the go and stop distances, such as slush, standing water, or snow. The effect of clutter must be measured for each airplane and published in the flight manual. Many levels of clutter have not been measured, so takeoffs on a cluttered runway are generally not legal unless the clutter effect has been determined. Notice that the effect of 4 inches of snow are similar to the effect of 8,000 feet of altitude. We'll now reduce the weight to 267,000 pounds and V1 to 123 knots, where a legal takeoff can be made on a 9,100-foot runway. To this point, we have looked at V1 strictly from an engine failure and legal takeoff perspective. Now we will look at some practical considerations, such as what if the runway is shorter or longer than the balanced field length, and what if the go or no-go decision is precipitated by events other than an engine failure, such as a fire or configuration warning. Let's consider a runway shorter than the balanced field length. First, let's look at the runway required for an all-engines takeoff. For these conditions, physically, a 7,300-foot runway would be adequate. However, for a legal takeoff, 15% must be added to the all-engines takeoff distance, for a total distance required of 8,400 feet. The greater of this distance, or the balanced field length, which was 9,100 feet, determine the legally required runway length. Let's take another look at the balanced field length condition, where V1 is 145 knots. Now let's assume that the runway length is 8,400 feet and try a takeoff with an engine failure recognition speed of 139 knots. Notice in this case we can stop, but we can't go. Now let's try an engine failure recognition speed of 149 knots. In this case, we can just about go, but we cannot stop. Now let's try an engine failure speed of 144 knots. What we have learned from this exercise is that if the runway length is less than the balanced field length, there is a range of engine failure speeds in which there is no safe option, since both the stop and go distances are longer than the available runway. In this case, an engine failure below 139 knots would allow a safe stop, and an engine failure speed above 149 knots would allow a safe takeoff. But an engine failure at any speed between 139 knots and 149 knots would have no safe result. This is not allowed for commercial operations. We should also note that for a runway less than the balanced field length, there can be no V1 defined, since there is no one speed below which you can stop and above which you can go. There is a separate stop speed and a separate go speed, with a range of speeds in between that have no good outcome. Now let's consider a runway longer than the balanced field length. Consider a 9,800-foot runway and an engine failure recognition speed of 139 knots. With an engine failure recognition speed of 139 knots on this 9,800-foot long runway, we can easily stop and just barely go. Now let's try a takeoff with the engine failure recognition speed equal to VR, which is 150 knots. In this case, we can easily go, but just barely stop. Now let's try to take off with an intermediate engine failure speed, 145 knots, which is the V1 for a balanced field length. Note that in this case, where the available runway is longer than the balanced field length, there are a number of speeds that meet the criteria for V1. In this example, where the available runway length is 9,800 feet, we could choose a V1 anywhere between 139 knots and 150 knots. A V1 of 139 knots provides the best safety buffer for stopping, while a V1 of 150 knots provides the best safety buffer for going. We know that a legal takeoff must have a runway at least equal to the balanced field length. Plus, we now know that if the available runway is longer than the balanced field length for our takeoff weight, we can select the value of V1 from a range of airspeeds. We should note here that the value of V1 for the balanced field length always lies near the middle of the range of allowable values of V1 and is therefore somewhat of an average. So what are the factors that would cause us to select a V1 different than this average value? First, we should realize that there can be many factors other than an engine failure that could activate the decision to abort. Second, there are runway conditions that can seriously affect the stopping distance more than the go distance. In order to abort the takeoff for almost any reason, we would like a runway long enough so that V1 could be equal to VR. On the other hand, if the runway is slippery, we would like to select the lowest possible V1 in order to minimize the stopping distance. Traditionally, the flight crew gets their value of V1 from charts or the flight management computer. The effect of this V1 on accelerate stop and accelerate go distances is usually unknown to them. For runways longer than the balanced field length, some airlines use the V1 for the balanced field length, and others use V1 equal to VR if the runway is long enough. In addition, computations are usually available to find a lower V1 if the runway is slippery. In all of these cases, the runway remaining after stopping or going is usually not known to the crew. Let's look at a specific example. Consider a takeoff on a 10,000-foot runway, using V1 equal to VR. The crew knows only that this runway meets legal takeoff requirements. If the crew had to abort and knew they would stop on the absolute end of the runway, they might select a lower V1. At the other extreme, selecting the lowest allowable V1 makes for a tight takeoff if an engine fails at V1. Here's an example. Luckily, computers can easily provide the full range of allowable V1s and runway remaining data to the crew, so that they can exercise their professional judgment and pick the best V1 for the existing conditions. Let's look at an example. This computer printout shows available V1 values for the existing conditions. For each V1 value, it shows the runway remaining after an abort and the runway remaining after the aircraft reaches 35 feet for an engine-out takeoff. Since the abort decision could be caused by many different reasons, the accelerate stop distance data does not involve an engine failure. Takeoff thrust is maintained until the throttles are brought to idle, which increases the accelerate stop distance slightly compared to the engine-out case. The data shows that with V1 equal to VR, there would be no runway remaining after an abort. In this case, the crew could choose a V1 outside of the yellow shaded areas, where the stop runway remaining would be at least 500 feet, and the go runway remaining would be at least 300 feet. This data shows that V1 equal to VR may be legal, but may not be a good idea. On the other hand, if the runway is 12,000 feet long, with the stop runway remaining being 2,000 feet, V1 equal to VR would not be a problem. What if the runway is slippery? A wet runway that is not cluttered has little effect on the accelerate go distance, but can seriously affect the accelerate stop distance. In this case, a low V1 can be selected in order to maximize the runway remaining if an abort is necessary. Some airlines refer to this as the slippery runway V1, but many have stopped using this terminology because the flight crew may interpret this to mean that they could make a safe abort at this value of V1 on any slippery runway. In reality, this low V1 only provides the maximum abort runway remaining, while still allowing an engine-out takeoff to be made. In this example, selecting V1 equal to 140 knots only says that 1,400 feet of runway remaining would be available if an abort was made on a dry runway. If the runway was covered with glare ice, 1,400 feet may be a small fraction of the additional stopping distance required. Complicating matters, there are more variables involved in stopping than in going. Apart from the runway surface condition and braking variables, delaying an abort decision at V1 for 1 second can add 250 feet to the stopping distance. The bottom line here is that many important choices are left to the flight crew's experience, and they need all the pertinent information to make the right decisions.